Hello and welcome to the first lesson in the topic amount of substance, and this lesson is about the mole, specification reference 3.1.2.2. and first of all, as usual, let's go over the learning objectives. And the first thing we want to be able to do by the end of the lesson is we want to understand the concept of a mole as applied to actually anything, right? For example, electrons. What's a mole of electrons? A mole of atoms, a mole of molecules, a mole of ions, a mole of ionic formulas, and equations too. So we want to understand a mole, and we also want to understand the related concept of the Avogadro constant, and we want to be able to use that constant to carry out calculations. Thirdly, let's carry out some of those calculations using the mass of a substance, its relative atomic mass, and also the amount in moles. So that, for example, might use the equation moles equals mass over mR, various derivations of that equation. Fourthly, we want to understand the concentration of a substance in solution as measured in moles per decimeter cubed, decimeter being a litre. And lastly, we want to do some calculations on concentration when given, for example, volume and amount of substance. So all those calculations will use derivations of concentration equals moles over volume. Okay, let's start, shall we? And first of all, let's ask ourselves, what is a mole? Well, in chemistry, a mole is a number, and that number is roughly 6.02 times 10 to the 23, right, which is also known as Avogadro's number or Avogadro's constant. And it's a number just like, say, a dozen is a name of a number, 12 in that case. So if we had a mole of carbon atoms, of carbon atoms, let's even say carbon 12 atoms, what would we have? We would have 6.02 times 10 to the 23 atoms. And if we had a mole of methane molecules, we would have 6.02 times 10 to the 23 molecules. Let's have a look at another example. What about sodium ions? Well, if we had a mole of sodium ions, we would have 6.02 times 10 to the 23 ions. And we could even have a mole of electrons or a mole of protons, in which case we'd have, guess what, 6.02 times 10 to the 23 electrons in this case. Okay, so collectively, let's call them particles. Okay, so then we can define a mole as roughly 6.02 times 10 to the 23 particles. And it doesn't matter what the particles are. In fact, you could have a mole of penguins if you wanted. And 6.02 times 10 to the 23 is a rather large number, isn't it? And so if, for example, you had that many atoms of carbon, what would it look like? Well, here's a picture of scales, and hopefully you can see that through the writing. And you can see on the scales we've got exactly, or at least we've got 12 grams to 2 decimal places, and 12 grams of carbon atoms, at least 12 grams of carbon 12 atoms, looks like what you've got there on the scales. So a handful, maybe a small handful of carbon atoms. So in that little pile of black carbon, there are about 6.02 times 10 to the 23 atoms, and they have a mass of 12 grams. and that's rather convenient, and it's convenient by design. It's convenient because a carbon-12 atom has 12 nucleons, i.e. 6 protons and 6 neutrons, and that's what makes it rather convenient when we do the calculations. So let's have a look at the Avogadro constant in a touch more detail, and why don't we write down the formula that we can get from the Avogadro constant. So if we wanted to know the number of particles in a sample, so they might be atoms, molecules, ions, whatever, the number of particles is equivalent to the number of moles times the Avogadro constant. Which you'll remember from the previous slide is 6.02 times 10 to the minus times 10 to the 23. Okay, should we do an example? Let's say you had 0.450 moles of pure iron, and the question would be, how many atoms are there? So how many atoms in 0.450 moles of iron? Well, it's quite easy. So atoms are going to be, so let me just write it like this, hash atoms is going to be the number of moles of atoms, which is 0.450, times the Avogadro constant, 6.02, times 10 to the 23. And if you punch that into your calculator, you'd get 2.71 times 10 to the 23. Easy peasy. Should we do another one? So this time, let's say you're told you've got a certain number of molecules of ammonia. So we've got NH3, and let's say we're told we've got 1.14 times 10 to the 24 molecules of ammonia, and we want to know how many moles of ammonia do we have. Okay, well, we've used the same equation, but we need to rearrange it. So if we divided both sides by the Avogadro constant, you get moles on its own, and on the other side of the equation you'd have number of particles divided by the Avogadro constant. And in number terms, we've been told in the question that we've got 1.14 times 10 to the 24, and then you would divide that by the Avogadro constant, 6.02 times 10 to the 23, and when you punch that into your calculator, you'll get 1.89 moles. Okay, hopefully that's quite clear. Simple 3-variable equation that you'll have to rearrange occasionally. So now I think we can do some calculations, some more slightly trickier calculations with moles. So when we're doing calculations with moles, I think the first thing to remember, probably from your GCSE days, is that 1 mole of any substance has a mass that's the same as its relative molecular mass in grams. Okay, so if let's say you had a substance X, and you have 1 mole of it, then its mass is equivalent to the relative molecular mass in grams. So if you looked at the periodic table and say you were interested in sodium, for example, it's Ar, because it's an element, it would be 23. Right, so if you had 1 mole of sodium, then by definition 1 mole of sodium has a mass of 23 grams. Okay, that's the first thing to remember. The second thing to remember, or the second thing to learn, that is, because you may not have come across this before, is a very important formula. All right, so it's so important I'm going to write it down. All right, so the number of moles of something, of anything, the number of moles of anything, is therefore equal to the mass of that substance divided by its MR, its relative molecular mass, or if it's an element it would be its AR, its relative atomic mass. Okay, that said, the easiest way to learn about this is to go through a couple of examples. So let's start off with the first example. First of all, an example that I'll do in red because it relates to our first little concept that we went through. So let's say you've got 1 mole of water. And you want to know what's the mass. You want to know what's the mass. Okay, so if 1 mole has a mass in grams equivalent to its MR from that you work out from the periodic table, then let's get the MR then. So the MR of water, H2O, is going to be 2 times 1, because 1's the AR of hydrogen, plus 1 oxygen. 1 times an oxygen's AR is 16. Okay, so the MR of water is 18. And our first statement was that the mass of 1 mole is equivalent to its MR in grams. So the mass of 1 mole of water is 18 grams. That's our answer. Okay, now what we might do is we might do an example in green because we're going to use the other equation that we wrote down. So let's say we've got a bit of aluminium oxide. So aluminium oxide, you might remember, has a formula Al2O3. So we've got Al2O3, we've got aluminium oxide, and let's say we've got 5.10 grams of it. So we've got a little sample, 5.10 grams of aluminium oxide, and our question is how many moles? How many moles? Okay, so the first thing we want to do is we want to work out the formula mass of aluminium oxide. I've called it formula mass because, of course, this is ionic. So the formula mass of aluminium oxide is, now there are, in each formula unit of aluminium oxide, there are 2 ions of aluminium. So we're going to have 2 times the AR of aluminium. Aluminium is 27.0. Okay, so that accounts for aluminium. And in the formula unit of aluminium oxide, there are 3 ions of oxygen. Okay, and the AR of oxygen is 16, as we know from the water example. So we're going to have 3 times 16. And so that's easy to work out, 102. Okay, so now we have the mass. Let me just change a little colour to, we have the mass, which is this one here in our equation. We have our MR, which is this one here in the equation. And our question is about moles. All right, so we can use the formula in green in the format that it's there as. So then the calculation is quite simple. So the moles of aluminium oxide is going to be the mass, which is 5.10, divided by the MR of aluminium oxide, which we worked out to be 102. And you put that into your calculator, and you're going to get 0.05. 00. Okay, question for you all. Why have I written it as 0.500? Why didn't I just leave it as 0.05? So if somebody can tell me that in class, I'd very much appreciate it. Okay, let's do another calculation. Let's say we've got sodium fluoride. And let's say we have 2 moles of sodium fluoride. 2 moles, and we want to know what the mass is. So what we're going to do is we're going to have to rearrange the equation. So in this case, we want mass of substance, this one here, to be on its own. And if we do rearrange by algebra, we'd have to multiply both sides by mR. Okay, so the mass is going to be mR times the number of moles. Okay, so in this case we're given the number of moles, it's the number 2, times the mR. Now the mR of sodium fluoride is we've got 1 atom of sodium in our formula unit. Sodium is 23, and we've got 1 atom of fluorine, and fluorine is 19. Okay, so if we together they add up to 42, so 42 is the mR of sodium fluoride, and 2 times 42 is 84. We better leave it as 84.0 grams. Okay, let's do one more example before we're finished with calculations with moles. But first, let's write our equation down so that we don't forget it. Our equation is number of moles. That's sometimes, or quite often, given the letter N as a shorthand way of writing number of moles, and that is mass over mR. So that's our equation, and while we're at it, why don't we write all 3 versions of it down? So you could have mR equals mass over N by multiplying both sides by mR and divided by N. Okay, and the other one is we would want mass on its own, in which case we would want to multiply both sides by mR to get N times mR. So they are our 3 versions of the same equation, and you could probably do them with a triangle as well. I don't know how the triangles work, but I see it written like this. For those of you who like triangles, you would have mass, and then you'd have moles times mR. So there's your triangle from which you can get these 3 equations if that's the way you prefer to do it. I'd recommend doing it by algebra personally, but maybe I'm old-fashioned. Okay, so let's do another example. Let's say you have 0.0500 moles of a solid, and that has a mass of 2.60 grams. Okay, and what you want to know is its relative molecular mass. So that's the question. And notice that we've got 3 significant figures here, and also 3 significant figures here. So let's make our answer to 3 significant figures as well. Okay, so if we've been given moles and if we've been given mass, but we want to find mR, why don't we use this version of the equation? Okay, so we've got mR is going to be mass, which is 2.60, divided by moles, which is 0.0500, and so we just plug that in to our calculator, and you get 52.0. to 3 significant figures. And there's your answer. Okay, so in class we'll do a bit of practice with those calculations, but for now, why don't we move on to concentration. Yes, and concentration is defined as how many moles of a substance are dissolved per 1 decimeter cubed of solution, and the units are moles per decimeter cubed. So let me just write that up here for you, moles per decimeter cubed. And like we said, we're dissolving stuff, in this case copper sulfate, in solution, in this case water, to make a copper sulfate solution. And as is suggested by the units, the equation that we use when we're doing concentration calculations is this. So the number of moles of copper sulfate, for example, or whatever substance, would be the concentration times the volume. And the volume would be in decimeters cubed. The concentration is in moles per decimeter cubed. And number of moles is just a number, usually given a shorthand notation N. So there's, in the same way as there was 3 versions of the previous equation, there's 3 versions of this. I'll just write them out for you. So we have concentration equals moles over volume, and that's the one I remember, and I worked the other 2 out from this one with algebra. But for completeness, let me write down the third one. So you'd want volume. Okay, so let's say what? So volume would be moles divided by concentration. And the volume units would be decimeters cubed. And the thing to be careful of is when the question is provided information for you, often they give the volume in centimeters cubed, and you're going to have to convert it into decimeters cubed. And that's easy enough, you just divide it by 1,000. So before we go on to do a few examples for you, let me do a triangle for you, just for those who prefer triangles to algebra. So if you have your triangle, you would have moles up top, and you'd have concentration times volume here. Concentration times volume, like that, in decimeters cubed. Okay, there's your triangle for you. If you prefer to use your triangle to work out whichever version of the equation you want, that's up to you. But in any case, let's do some examples. So first example, we've got some lithium chloride solution. So we've got lithium chloride solution, and we're given the concentration. Concentration is 1.2 mole per decimeter cubed, and we're given the volume as 25 centimeters cubed, and the question wants us to work out how many moles of lithium chloride. That's what the question is asking us for, and let's do it. Do the answer in red, shall I? Okay, so first of all, why don't I just write our 3 equations up here. So the one I start with always is concentration equals moles over volume, and so from that I can see that moles equals concentration times volume, and volume equals moles over conc. Okay, so there we have our 3 equations. We're going to use one of those. Let's see. So the question is asking us for number of moles, so we'd probably use this middle one here because we're given the other 2. So moles of lithium chloride equals, concentration 1.2 moles per decimeter cubed times the volume. Now notice we've been given the volume in centimeters cubed, and our concentration is per decimeters cubed. Right, so we're going to convert 25 cm cubed into decimeters cubed, and all we do is we divide it by 1,000. So it's 25 over 1,000 decimeters cubed. And just to make that logical for you, this is 1 centimeter cubed. Yeah, so that's 1 centimeter, and that's 1 centimeter, and that's 1 centimeter. So that's 1 centimeter cubed. Now a decimeter would be about this big. I'd have to, right, decimeter is going to be 10 centimeters by 10 centimeters by 10 centimeters by 10 centimeters, and it's going to go back into the page like that. Right, so that's going to be 10 cm cubed. That would, sorry 10 centimeters. That's going to be 10 centimeters, and that's going to be 10 centimeters. And the volume of the big box, volume big equals 1 decimeter cubed. Decimeter for 10. And so you can see that you're going to need 1,000 of these. Just change color. 1,000 of these, right, to make 1 of the big cubes. Okay, so that's the logic behind this little equation here. So going back to the calculation, switch back to red. Our volume is going to be in decimeters cubed. It's 25 over 1,000 decimeters cubed, and so when we plug that into our calculation, we're going to get 0.03 moles. Should we leave it like that? We could do that many moles, and that's the answer to the question there. Yeah, just for completeness, you noticed me adding an extra 0 onto the end of the answer there, and it's because our question gave us concentration in 2 significant figures, and our volume was to 2 significant figures as well, so we gave our answer to 2 significant figures. Okay, let's do another simple example. Let's try and fit it down on this section of the paper here, and all this other example is going to do is going to use one of the other versions of the same equation. Okay, so let's say this time we've got some iron chloride solution, and we're told that the solution contains 0.2 moles. So N equals 0.2 moles of iron 3 chloride. That's just a different way of writing the molecular formula. And we're told that those 0.2 moles are dissolved in 0.4 decimeters cubed. Alright, so that's telling us the volume, 0.4 decimeters cubed, and they've even given us the volume in decimeters. So easy peasy, let's do it quickly. Okay, so it's asking us for, let me just switch back to blue because I've not told you what it's asking us for. So it's asking you for the concentration, of course. So it's asking you for the concentration, in which case we'll probably use this version of the equation. So concentration is going to be number of moles, which is 0.2, divided by the volume, which is already in decimeters cubed, so we just do 0.2 over 0.4, and so you can quickly see that that is 0.5 moles per decimeter cubed. Okay, there's another example. We might do another simple example before we do a realistic example. Okay, so our last simple example involves zinc sulfate. as a ZnSO4, and if we were told that you've got 0.080 moles of zinc sulfate, and in a solution of concentration 0.50 moles per decimeter cubed, it's asking you for what volume is that solution. What volume of that solution would be if you've got if it's concentration 0.50 and you dissolve 0.080 moles in it. Well, okay, let's remind ourselves of the equations. So the one I start with always is the intuitive one, which is concentration equals moles, it's supposed to be an N, over volume, and from that I get N equals conc times volume, and volume equals N over conc. Okay, so we're going to use the third version of this equation. So our volume of zinc sulfate solution is going to be equal to the number of moles, which we're given in to two significant figures, 0.080, divided by the concentration, which is also given us to two significant figures, 0.50, and because the concentration is in decimeters cubed, the units of our volume is going to be decimeters cubed, and if we put that into our calculator, we of course would get, and we wouldn't need a calculator for this, would we, but it's easy to see that the answer is 0.16 decimeters cubed, because moles is moles and moles is moles, and the volume in the concentration was decimeters cubed. Right, and the question might say might want to specify the volume in centimeters cubed. Right, so if it's 0.16 decimeters cubed, you're going to multiply that by 1,000 to get the centimeters cubed. So you just take your decimal point along 3 places, so you get 160 centimeters cubed. Okay, so that's the third version of the equation. Just plug it into numbers into a 3-variable equation, pretty easy. And to be honest, it's not realistic that you're going to get one of those in the exam. In the exam, you're much more likely to have to combine the last 2 equations that we've done, i.e. the one 4 slides back and this one here. So let's do an example of a realistic equation. So here's the question. What mass of sodium hydroxide needs to be dissolved in water to give 50 centimeters cubed of a solution with a concentration of 2 mole per dm cubed? Okay, so let's work through that. So the first thing that I'd notice when I was doing this question is it's asking you for mass, and that always, nearly always, suggests that you're going to use your conversion between mass and moles formula. If you look at the rest of the information that's in the question, it's talking about concentration, right? It gives you the number, and it's talking about volume, and it's given you 50 cm cubed. Notice cm cubed, not dm cubed. Okay, so if you just get in your helicopter for a little second and plan out the question before you started, you can see that you've got volume and you've got concentration, so you can quickly work out moles using the equation that we've just used on the previous slide. And if you have moles, then you can quickly convert that to mass using the MR of sodium hydroxide. So that's the plan for the answer. Let's just work through it. Okay, so we're going to say let's write our little equations out for first. So for me, I'm going to put concentration equals moles over volume up here, so that when I'm looking at this and I see I've got a volume and I've got a concentration, I can then say moles of sodium hydroxide, right, is going to be concentration times volume. Okay, so the concentration is given in moles per decimeters cubed, so that's fine. So we're going to write our 2.00 in here, and our volume is given in cm cubed. So what we'll do is we'll put our 50.0 there, but of course we want to deal in decimeters cubed, so we're going to divide that by 1,000. And so the moles of sodium hydroxide that you're going to need is 0.1. But we want three significant figures, so we're going to say 0.100 moles. And we've not got units because it's just a number of moles. Okay, so that's the moles of sodium hydroxide, but the question, of course, is asking for us the mass of sodium hydroxide. So in order to convert moles to mass, we're going to need to know our relative formula mass of sodium hydroxide. So we can write that like that, and then we have to refer to our periodic table, and we're going to add up the atomic masses of sodium. Okay, 23, and you look at your periodic table for your atomic mass of oxygen, of course 16, and hydrogen, let's say it's 1, and you add those up and you're going to get 40. And actually our periodic table gives us one decimal place as well, and as it happens they're all to 0.0, so we can say that this is 40.0, and then we're being consistent with the three significant figures that we need to work to. Okay, so there's our MR. Remind yourself of what the equation is that we need. The version of it that I remember is moles equals mass over mR. Right, so if I keep that one in my head and then I just work out the others from it, rather than having to remember three equations. Okay, so, but what we want is we want mass of sodium hydroxide to answer the question. Alright, so we can quickly see from that equation I've written in red that mass is going to be the number of moles of sodium hydroxide, right, times the mR of sodium hydroxide. Okay, so moles, we've worked out in the first part of the question was 0.100, and the mR we've just worked out there, which is 40.0, and so you can quickly see that the mass is going to be 4 to three significant figures is 4.00 grams. And there we are, and that's the type of question you'll get in an exam where you have to combine the two different amount of substance equations there, the two that are written on in red on the page there. Okay, hopefully that's been clear. Let's just check before we finish that you're okay with all the lesson objectives. So quickly, our learner objectives were: we wanted to understand the concept of a mole as applied to lots of different types of particles. I think we went through that. And we wanted to understand the concept of Avogadro constant, 6.02 times 10 to the 23. And we calculated numbers of particles and such like. We carried out some calculations using mass of substance, mR, and amount in moles. And you remember that equation, moles equals mass over mR. That's the calculations we did with that equation. And then we understood that the concentration of a substance was measured in moles per decimeter cubed, and we carried out some calculations using concentration, volume and amount of substance, i.e. moles, and that was the concentration equals moles over volume equation and its variance. So not only we did that, but we also combined those two equations to do a slightly more difficult question there. So we've covered those learning objectives. Hopefully they were clear for you. If not, you need to let me know. But in any case, I'll see you very soon.